Welcome to the final lecture of Math 320. In this final lecture, we will talk about L'Hopital's rule. This material is given on pages 242 through 244 on your textbook. Hopefully, the phrase L'Hopital's rule is not foreign to you. You have seen it in Calculus 2 when we introduced it as a way to evaluate limits of ratios of continuous functions when the limits are in indeterminate form. What we will do in this lecture is to justify L'Hopital's rule using the mean value theorems as crucial ingredients. Let's get started. Let's start by stating the theorem. To properly apply L'Hopital's rule, there is a list of hypotheses that must be verified. We're given two functions f and g defined on an open interval ab. We assume both f and g are differentiable at every point in ab. We assume that g prime is not 0 anywhere. We assume that the limits of f and g as we approach the top endpoint b from below both equal 0. Notice that we do not require f and g to be defined at b. It is enough that one-sided limit exists. And finally, we require that the limit as we approach b from below of the ratio between f prime and g prime to converge to some value L. Once all these assumptions are verified, we can then conclude that the limit as we approach b from below of the ratio of the original function f over g also converges to the same limit L. Here are some important notes about L'Hopital's rule. First, the functions f and g that appear in the theorem need not themselves be defined at b. It only needs to have a one-sided limit as you approach b. In the hypothesis, we require g prime to be non-zero on the interval ab. This is required to ensure that the ratio f prime over g prime makes sense. In calculus classes, this is often not emphasized strongly since in the examples you computed in calculus classes, usually g prime turns out to be non-zero in some interval surrounding b, simply because calculus classes often only deal with simple functions. To be fully applicable to more general functions, we need to explicitly add this non-vanishing condition to our hypotheses. At this point, you may ask, but we have the conclusion that the limit of f over g converges. What if f over g fails to make sense? It turns out, as part of the proof, we will show that g is not 0 either, and so f over g also makes sense on the whole interval ab. Finally, we say L'Hopital's rule for the one-sided limit converging to b from below. L'Hopital's rule also holds for the one-sided limit converging to a from above in the interval ab. More generally, we can even that a domain to be infinite. If the domain is the interval from a to infinity, if we replace the one-sided limit from below to b everywhere by the limit to positive infinity, the same statement works. Similarly, if the domain is the interval from minus infinity to b, we can look at the limit towards minus infinity. Again, since our emphasis is in understanding why is L'Hopital's rule true and not cramming into your heads all the possible variations of L'Hopital's rule, I will limit the discussion in this lecture to the case where we're taking the limits to b from below. When reviewing this material, it may be helpful to try and see if you can mentally mark out all the parts of the proof that needs to be changed to address the other versions. We will begin with a discussion of the basic proof idea. First, we will pretend that f and g are both defined at the point b and are equal to their limits. In other words, they are both 0 there. For an x in the domain, we can then try to rewrite the ratio f over g. First, as f of x minus f of b divided by g of x minus g of b, using that f of b and g of b are both 0. And then, as the difference quotient of f centered at b divided by the difference quotient of g centered at B. Next, if we pretend that f and g are both differentiable at b, remember, we don't require the function to be defined there, and certainly not that they are both differentiable. But if we pretend that f and g are both differentiable at b, then as x approaches b, the difference quotient should converge to the derivative, and so the ratio of the difference quotients should converge to the ratio of the derivative, which we hope is the same as the limit of the ratio of f prime over g prime as x approaches b. So why is the previous slide illegal? Firstly, the functions need not be defined at b, and we made no assumption that their derivatives exist at b either. And the situation is even worse if we were looking at the infinite case, instead of the case of the limit going to b from below. In the infinite case, the difference quotients don't even make sense. Even accepting that f has a limit at infinity, trying to form the difference quotient f of x minus f of infinity divided by x minus infinity just doesn't make sense. Our goal is to reformulate the illegal quote-unquote proof that we just wrote down in a way that every step is replaced by something justifiable. Here is the proof. First, recall all the hypotheses. Remember, the important ones are that g prime is non-zero, that f and g have limit 0, and the limit of the derivative ratio exists and equals L. We divide the proof into several steps. The first step, we prove that the ratio f over g makes sense by proving that g cannot be 0. First, we notice that an application of the intermediate derivative theorem tells us that having assumed g prime is non-zero, we can conclude that g prime is either always positive or always negative. Why is this the case? Because if g prime, the derivative, were such that it is positive somewhere and negative somewhere else, then the intermediate derivative theorem would tell us that since 0 is a value between any positive and any negative number, that at some intermediate point, the derivative of g must vanish. But we have already assumed that g prime is never 0. Since g prime is always positive or always negative, this means that g is strictly monotonic on its domain, either strictly increasing or strictly decreasing. We proved this fact in lecture 2 this week. Now, if g were strictly decreasing and we know its limit is 0, this would mean that g has to be positive for every x in the interval ab. If g were strictly increasing and we know its limit is 0, this would mean that g has to be negative for every x in ab. So in either case, g itself can never be 0 on the interval ab, and hence f over g makes sense. You should also remember in this step, we have proven that g is strictly monotonic, which also ensures that g is an injective function. Next, our goal is to prove that f of x over g of x has a limit. Our input information concerns f prime of x over g prime of x. We need to convert from the functions to their derivatives in order to pass the buck. So in this second step, we will perform this conversion. For this, Cauchy's mean value theorem is very useful. We proved this in lecture 2 this week. If f and g are both differentiable on an interval, then there is an interior point where the derivative of f times the total change of g is equal to the derivative of g times the total change in f. So now let x and y be arbitrary in the interval ab, labeled so that x is less than y. Since we know that g is injective by step 1, the difference g of y minus g of x is non-zero. our hypothesis on G also specifies that G prime is not 0. This means we can safely cross-divide to rewrite the conclusion of Cauchy's mean value theorem in ratio form. This says that the ratio of the total change of f and the total change of g is equal to the ratio of derivatives for some z between x and y. So, as I mentioned at the first lecture of this week, this is where the mean value theorem is very useful. It allows us to transfer information about derivatives to information about the functions themselves. This time, we use the Cauchy version to do this work. Next, we will use the limits. Remember them? In the hypotheses of this theorem, we assume that several limits exist and gave their values. First, we will use the fact that the ratio of derivatives have a limit. This means that given any epsilon positive, we can find a delta positive such that if z is inside the interval from b minus delta to b, the difference between the derivative ratio and L is less than epsilon. Now, returning to how we passed from function to derivatives in the previous slide. There, we chose x and y to be arbitrary between a and b. If we were to be more picky and select only x and y from between b minus delta and b, then, since z is also between x and y, the resulting z would also be between b minus delta and b. So, combining the fruit of step 2 with the convergence of this derivative ratio, we see that whenever x less than y are 2 points between b minus delta and b, then the ratio of the total change of f divided by the total change of g is no more than epsilon from L. Finally, we can expand the absolute value in the inequality and write it as the ratio of the total change of f divided by the total change of g is between L minus epsilon and L plus epsilon. This is under the assumption that x and y are both between b plus delta and b. B minus delta and b. Now, we can use the other limits. Previously, we used the limiting property of the derivative ratio. Now, we will use the fact that f and g themselves have limits. On the top, we recorded what we have found on the previous slide. Now, for the moment being, consider x as a fixed number between b minus delta and b, and we will take y as a variable and move it toward b. Since this makes y larger and larger, y will remain bigger than x. And so throughout this process, the inequality shown on the top of the page will still hold. If we look at f of y minus f of x, for a fixed x, taking the limit as y approaches b from below, just converges to minus f of x, since we know that f of x is fixed and independent of y, and f of y converges. Similarly, g of y minus g of x converges to minus g of x as we take the limit as y approaches b from below. So, we have a ratio of two functions, both of which converges as y goes toward b from below. So from what we learned about arithmetic of limits, the limit as y approaches b from below of the ratio is the ratio of the corresponding limits. And so the limit is exactly equal to minus f of x divided by minus g of x. On the other hand, by using the comparison theorem for function limits, since the terms of the ratio are always between L minus epsilon and L plus epsilon, this means that the limit must be between L minus epsilon and L plus epsilon also. Notice that Notice that when applying the comparison theorem only holds for non-strict inequalities. So our conclusion has to be L minus epsilon is less than or equal to F over G, which is in turn less than or equal to L plus epsilon. So what do we conclude now? We have demonstrated that for every epsilon positive, we can find a delta positive such that whenever x is between b minus delta and b, the value of f of x divided by g of x is between L minus epsilon and L plus epsilon. Not strictly, but we can fix it by renaming everything we called epsilon up to now 1/2 epsilon. In any case, this final conclusion is precisely what it means for the ratio f over g to converge to L as x approaches b from below. And this is the conclusion we hoped for from L'Hopital's rule. Just to reinforce what we did now, let's go back to the illegal proof that we started out with as the motivation. We pretended that f and g are defined at b with value 0, which is illegal. We performed some computations based on this illegal assumption, and we argued illegally that taking the limit as x goes to b will give us the non-existing ratio f prime b over g prime b. What we did in the proof before can be regarded as trying to fix the proof by replacing b first with something very close to b. We used that the limit of f and the limit of g are both 0. So we saw that the ratio of f over g is up to a small error, the same as the changing f over changing g over the interval from x to b minus delta, where delta is very small. So f of b minus delta and g of b minus delta are both very close to 0. Then we use this to form difference quotient. Now there are some errors to contend with in the very first approximation. But let's forget it for the time being and just focus on the difference quotient we just wrote down. If we can take the limit as x goes to b minus delta of the difference quotient, since this is now firmly within the domains of f and g, this limit actually converges to f prime of b minus delta, provided g prime divided by g prime of b minus delta. To summarize, this suggests that for all sufficiently small delta, we should have that the function ratio f over g to be approximately the same as the derivative ratio f prime over g prime if we evaluate at b minus delta. As delta goes to 0, the right inequality goes to L by hypothesis. So what we need to show is that the error in this particular approximation also goes to 0 as delta goes to 0. The control on this error is what is the meat of this proof. And this is precisely what we did in steps 3 and 4 of the actual proof shown earlier. So we have come full circle. At the beginning of this course, I mentioned how the goal of this course is for you to see the underbelly of calculus, to see how to make sense of reasonings that is based on intuitive expectations of what are infinitesimal quantities. Earlier in the semester, we discussed the completeness of the real number line and showed how it possesses the Archimedean property, and hence there are no such things as infinitesimals. The remainder of this semester, we spent talking about how to build up calculus by replacing things having to do with infinitesimals by a rigorous understanding of limits, sometimes using the epsilon delta arguments. In these few final slides, what we just did was write down the infinitesimals version of the proof of L'Hopital's rule. As we know, this proof is largely fiction due to the lack of infinitesimals. But as we also just saw, a sketch of the infinitesimals idea can often be turned into a proof using properties of limits in a proper way. the infinitesimals are not useless. They are useful guides to what we can expect to be true. But on the other hand, to actually deduce that our expectations are in fact correct based on how we have construed the mathematical universe to be, we have to work to replace the infinitesimals in the arguments by limits that are actually compatible with our understanding of the real numbers. And the circle of ideas is what we call, in mathematical practice, the subject of analysis. And with that, thanks for watching and listening, and congrats for making it this far. Ciao.